So I'm now doing a request session for AQMF. I've just finished integration and I've been asked to go over implicit differentiation. I'm going to break the only sharpener. I put 4 new sharpeners in the Maths Learning Centre last week and there's only 1 left. So just let me have a quick look at your lecture notes to see what your lecturer said about it first. Because I could tell you stuff, but it might not be what's in your course. I can't. Oh, there it is. Okay. All right. So you have something along these lines. Give me a second. So, we've got It's not going to work, is it? Okay, that'll work. Okay, so find dy and dx when x is equal to minus 10 on 3 and y equals 0. Or if you like, the point minus 10 on 3, 0. The reason that took me so long is you actually have to find a set of x and y that actually satisfy that equation. So that was the hard bit for me. But you wouldn't have to do that. We're up to here. Okay? Okay, you can actually just be told the x, as long as you can sub it in there to figure out what the matching y is, it'll be okay. All right, so find dy on dx when that's the truth. So implicit differentiation says that supposedly it is possible at this point to rewrite y as a function of x, to write y equals some sort of formula involving x. Okay, and in some other economics and finance maths courses I have seen, they actually give you a theorem that says, yes, that is true. So you're not told that, but it is true. It's possible, it is technically possible to find some sort of formula. It may be sufficiently ridiculously horrible that would rewrite y as a formula in terms of x. Okay, so that means it must be possible to differentiate y in terms of x. So instead of finding that formula, we're just going to differentiate y in terms of everything in terms of x. So, all right, differentiate original equation with respect to x. That's what we're going to do. So we're going to have to use the product rule and the chain rule. So when we look at this bit here, we have 2 things multiplied together. We have x and we have y cubed. The y is a formula, is a function of x. There is some formula that goes in that spot that involves x. So I can't just do, like with partial derivatives, I can't just pretend y is a constant. Because it's not, it actually changes when x changes. So I need to say, all right, the product rule would say I would need to do the derivative of the x and keep the y cubed. I would keep the x and differentiate the y cubed. So the derivative of y cubed would be 3y squared, but that y is actually a formula involving x, so the chain rule says I have to do dy on dx as well. So whatever is inside there, I have to multiply by its derivative. Okay, so that's the derivative of that part. So now the next bit, I'll differentiate that. So I'll differentiate the minus 2x squared, which is minus 4x, and I'll keep the y squared. And then I'll keep the minus 2x squared, and I'll differentiate the y squared, which would be 2y times the derivative of y because of the chain rule. Finally, the differentiation of that with respect to x is minus 3, and the differentiation of that with respect to x is 0. Okay, so now each part of it, these two parts I had to use the product rule for, but each part of it I have now differentiated. Okay, so now I need to get a formula dy on dx equals, because that's what I was trying to find. I was trying to find dy on dx. So I'll just rewrite this to look prettier first. So I've got y cubed plus 3xy squared dy on dx minus 4xy squared minus 4x squared y dy on dx. So this is what I'm looking for, the dy on dx. So I'll keep everything involving dy on dx over this side and put everything else over there. So I've got 3xy squared dy on dx minus 4x squared y dy on dx is equal to, so that will become a plus 3, that will become a minus y cubed, that will become a 4xy squared. And now I want a single dy on dx, so I can factorize. And finally, to get the dy on dx its own, I can divide by that. Okay, cool. And so now I know that when x is minus 10 on 3 and y is 0, dy on dx will be 3 minus 0 plus 0 because there's y's in that. And they're both 0, so it doesn't actually exist at that point. Damn. Picked a bad example there, didn't I? But that's okay. That means that it's actually vertical at that spot. So, so we have that it does not exist, i.e. the tangent is actually vertical at that point. But if I had chosen a y that actually worked, I would have actually been able to come out with something, hopefully. So there is a point there on the curve. It's just that the tangent's vertical at that spot. So I might just, as a final example, figure out another point that's actually on there. Really? Oh, I can't. Too hard. I can't choose x equals 0 because that won't have a derivative either. I'd really like to choose both x and y to be 1, but that's not actually on that curve. So just not doing well there. I should actually probably draw it, get a computer to draw it and ask one of the points. But I could technically now at any point figure out what the slope would be if it did go through that point. So when x and y are both 1, I can figure out that I get 3 minus 1 plus 4 over 3 minus 4, and that would give me an answer. Yeah, is that all right?
Yeah.
Cool. So if you're actually specifically asked for the formula for the tangent, then you need to go like y equals ax plus b, with the a being that slope. Yes?
How is it possible for the derivative to be defined, say both x and y equals 1, but x and y equal 1 want to be on that curve?
The formula of 3 minus y squared plus 4xy squared on 3xy squared minus 4x squared y is perfectly well defined for many x's and y's, but it doesn't represent the derivative of that curve for a lot of points. My suspicion is that it would actually be the slope of the tangent that goes through that point, even if that point's not on the curve. So you might be able to draw a tangent from that point to the curve, and it would probably be the slope. I have no guarantee that that's the truth, though, but that would be my instinct. So yeah, this is a perfectly well-defined formula for a whole lot of x's and y's that just might not actually be on the curve. So I just couldn't think of one. All right. Any other questions about anything in the course?
With assignment 11,
Yeah, I've actually got assignment 11. Yep.
with the DEs, I'm not really sure how to do this.
So generally, okay. Cool. So there are many, many different kinds of differential equations, and in each course in first year, no matter which one you're doing, you're only told about a few of them. As differential equations are hard to solve, mainly because integration is hard. So you know what a differential equation is, so i.e. an equation that's got a derivative in it. The aim is to find a formula for y in terms of x. Okay? Aim. Okay, that's the aim. Y equals some sort of formula in terms of x. The problem, so with ordinary equations, you want to find out what x and or y are, but this, a differential equation, you're trying to find a function. Okay, you want to say which function y differentiates to go into this formula to produce this answer. Okay, so I'm just going to run through this and talk through how they work. Just like with the techniques of integration, there are techniques of differential equation solving, and so you've been told about just doing it and separable differential equations, as far as I'm aware. So, so our techniques, which I've spelt correctly this time, sort of just integrate it and separate, so separable equations. Okay? And there's sort of a technique -1, which is have an answer already and check to see if it's correct. Okay? So so there are techniques. So let me just run through this assignment 11. Not all of it, but as much as I can do. So assignment 11, question 1a says, is y equals 4x cubed plus 2 a solution of this differential equation? Okay, so you do not have to use any of the techniques because all you've been asked is the answer true? So if you were asked, is 3 a solution of x squared minus 9 equals 0, you would just sub it in and see if it worked. And that's precisely what we're doing here. But the thing we have to sub in is a formula to sub this formula in for y, and whatever the derivative of that is in for dy on dx. Okay, so first we have to figure out what dy on dx is. So that's my question. So that's 4 times 3x squared, and the 2 is 0, so 12x squared. Okay? And so then I'm going to actually sub this in. And I sub it into the left-hand side, and if there's anything to sub in, I sub it in the right-hand side, and I see if the answers come out the same. So we'll say that the left-hand side of my differential equation is x dy on dx minus 3y, which is x, and dy on dx is 12x squared, and y is 4x cubed plus 2. So I sub them both in, and so what I get is 12x cubed minus, so let's see, 3 times 4 is 12x cubed, minus 3 times 2 is minus 6, so I get minus 6, which is the right-hand side. So, technically, and so therefore, yes, it is a solution. Those of you in Maths 1A have this to look forward to in Maths 1B. Okay, I'm going to do another one just to show you one that's a little more complicated. Okay, so is y equals 5e to the minus 3x plus 2e to the 2x a solution of this differential equation? Now, you don't have techniques for solving that. They don't even do that in Maths 1B. I'm not even sure if they do that in differential equations too. I'm sure they do. But you do have a way of checking to see if the answer is right. We need the first derivative and the second derivative. So let's see. dy on dx. So the derivative of that, the 5 will stay there because it's being multiplied, and we'll have to go e to the minus 3x, and because we're differentiating, we'll have to multiply by that minus 3. And then the 2 will stay there, and the e to the 2x, and because we're differentiating, we have to multiply by the derivative, which is 2. So like that. Awesome. And then the formula has the second derivative as well, so we'll have to calculate that. So minus 15 will stay there. We'll already did that derivative up there. Okay, so we've got 45 e to the minus 3x plus 8 e to the 2x. Okay, and then we sub both of those into the other formula. So my left-hand side is d squared y on dx squared, which is this. I'll just write it again. So my left-hand side was this. The second derivative is here. Yep. And then I've got minus 6y, and y was equal to this. So I'll do my best to make that look as simple as I can. Minus 30 e to the minus 3x minus 12 e to the 2x. So I've just expanded out those brackets. So 45 of these minus 30 of them, so 15. And this minus that is... Okay, so the right-hand side is minus dy on dx, which is minus 15 e to the minus 3x plus 4 e to the 2x, which is 15 e to the minus 3x minus 4 e to the 2x, which is the left-hand side. because they're the same. So yes, it is a solution. Okay? Is that all right? So this is the clearest way of showing that a solution is actually a solution, subbing into left and right. And if these hadn't come out to be equal, I would have said, no, it's not a solution. This is the same question as verify that this is a solution. It's the same question. Verify just means check. Verify literally in English means establish the truth of. So establish the truth of the statement that this is a solution, which means sub it in and see if it works. The problem with differential equations is you have to differentiate it before you sub it in. Okay? So, working my way down. Let's do question 2. So question 2a says, find the general solution of Okay. So I want to add something. I want to add something to what I said before in my techniques. Back in my techniques, you may have to rearrange it to make it look like these techniques. So just as a star, might need to rearrange. Okay? I say that because this one requires me to rearrange. So you might need to rearrange it so that it's just integrate it is when you can have dy on dx equals and everything over here is in terms of x. Okay? And separate is when you've got x's and y's. Okay? And you'll be able to separate it to get y and dy over here and x and dx over here. Right? So technically, if you can separate and there's only a dy left, then you could have just integrated it. Okay. So with this one, I'm looking at it, I'm saying, look, these are all x's. If I just put them over here, I'll get dy on dx equals, and everything will be in terms of x. I'll just get that. So I've just put all of this over there. So now it's just the derivative is equal to that. I just have to integrate it and that will be the answer because I just have to undo that derivative. So integrate and I'll get y equals whatever the integral of this is. So e to the 14x, well, that would be the same, but because I'm integrating I have to divide by the constant. The integral of minus 5 is minus 5x. The integral of 1 over x would be ln x, but it's 11 times 1 over x, so it's actually minus 11 ln x. And the integral of that, well, the minus 5 will stay there. I'll put the power up by 1 and it'll go up to minus 3, and I'll divide by minus 3. And because I'm integrating, there will be a great big plus c, because I'm trying to find all possible formulas for y that would differentiate to go into this formula. So 14th e to the 14x minus 5x minus 11 ln x plus 5/3 of x to the minus 3 plus c. And that's what they mean by a general solution. It will have an unknown in it. I mean, x is a variable and not an unknown. It'll have a constant that you do not know somewhere. Okay, so that's the general solution. So this was in the category of just integrate it. So rearrange it and just go, oh, cool, it's just all in terms of x. I'll just integrate it. So the other situation happens with part C of that question. Which is that. So it's asked to find the general solution again. So this time I have to rewrite it in such a way that I can separate the x's from the y's. And that all has to be done with multiplication and division. So I'm not allowed to add or subtract because I need to arrange for it to be something times dy so that if I whack an integral sign on it, it will become an integral. Okay? So just like in substitution where you sort of ignore the integral sign and treat everything else like stuff that you can multiply together, that's what we're doing here. So I want to put all the y's and dy's over here and all the x's and dx's over here. So I will multiply both sides by y to the 6. And I'll multiply both sides by dx. You can do that in one go if you like. And now I have that y to the 6 times a small change in y is equal to x to the 5 plus 7 times a small change in x, and I can whack integral signs on it to now do the integral. So I'll do the integral of each side separately. So okay, so the integral of this is it's in terms of y, so I don't have to worry about any of the x's. So the power will go up to 7, and I'll divide by the new power. And this power, this I can integrate in terms of x. So this power will go up to 6, and I'll divide by the new power. And this 7 will go to 7x. And there'll need to be a plus c. You don't need to put a plus c on both sides, because technically they won't necessarily be the same constant. You might need to put a plus c here and a plus d here, but then you could put them over the other side and combine them together and they'd just be a new constant. So we only need one of them. But the point is I actually haven't finished yet because I'm supposed to get to y equals, if you recall. So when I do, see, the aim is to get y equals formula in terms of x, and I don't currently have that. I have a 7th of y to the 7 equals that. So you can imagine how you could possibly get this formula via implicit differentiation. So we got a formula very like this from implicit differentiation. And so what we're trying to do is sort of do implicit differentiation backwards. But we're also trying to, so we've done the implicit differentiation backwards here, but we're also trying to solve this to figure out what y is. So, yeah. So, now we need to get y on its own. So the time-honoured fashion of starting as far away from the y as I can. The 7 is, the power of 7 is closest. I'll get rid of this 7th by multiplying both sides by 7. Okay, but oh, I didn't actually multiply by 7. That was bad, wasn't it? Okay, multiplying everything by 7. But technically that 7c is just a new constant. If I have, because c could be everything, 7c also covers everything, and so it's fine to, at this stage, give that a new name. I've just called it a new constant because it looks prettier. Some people would call it plus c again, but that freaks me out, so I like to change the letter. And now finally I need to get rid of that power of 7. So I technically need to do the 7th root to get rid of that. And another way, alternative way is to do it to the power of a 7th. So in the same way that square root would be power of a half, 7th root is a power of a 7th. So I could do power of a 7th on both sides. Like that. And you'll notice that the plus d is trapped inside this bracket. That's important. You need to put the plus c in at the moment the integral signs disappear, otherwise the answer will be wrong. So the constant is trapped inside that bracket. Okay. So let's do 4a. No. Let's do question 6. I've only got 10 minutes to go, so I want to pick one that does everything I want. Yep.
Just quickly with the 7c, you
Yep.
can use that as 7c the whole way.
That'd be perfectly fine.
That's fine.
Yeah. But I just like to change it into a constant, because if I was going to have to sub in things to figure out what that constant was, it'd be easy to figure out what d was than to figure out what c was, because you'd have to divide by 7. So if I knew that when x was 0, y was 1, I'd get d to the 7th equals 1. So d would be 1, and I don't need to know what c is. So that's why I do it. Whereas c would be a 7th, and that's not nearly as nice. So yeah, that's why I do it. And I'm really hoping that this next one will give me a chance to show something. So okay. Oh, and also, now sometimes there's a plus c, but sometimes you've got extra information that will tell you what that c is. And so this one has y of 0 equals 1. It'll often be 0, that's the one that you know, because in practical situations that's usually the one that you actually know the answer to, and you want to figure out all the rest. So especially in things like engineering, but it's also for, because you know what it is, most of these are about trying to predict what happens in the future. You use differential equations, tell you how things are changing now, and you want to know what the formula is in 10 months' time. So you want to know what the answer is in 10 months' time. So x would be time, and y would be, you know, produce or capital gain, or the you know, gross national product or something. And so you know what it is now, because that's 0, and you want to know what it is in the future. So that's why 0 is the most common one. So we're going to run with separating it. So we need to put all the y's with the y's and all the x's and dx's with the x. So if we divide both sides by that, that'll get the y's off of this left-hand side. And then we can multiply both sides by the dx. And now I have all the y's on one side and the dy, and all the x's and the dx on the other side. And now I want to do the integral. But the problem is, I don't know how to do that integral. This one I can do. It's a third of x cubed. This one, well, now I need to go back to using my techniques of integration and think, all right, can I rewrite it? No. Substitution would be the next thing to try. So I need to find something that I can call u, and I'll pick the most annoying bit, which is this on the bottom. So I won't even put the integral signs in yet, because I want to rewrite this in terms of u. U is y squared plus 3. That's the most annoying part. So du on dy is 2y. And so du is 2y dy. So you'll notice that we have a 2y dy already, because if we think of that as a fraction, on the top of my fraction I have a 2y dy. So that 2y dy becomes u. So I now have that the 2y dy is in fact u. This is in fact du. And this is u. So that's what we have now. And we can integrate that, because that's the same as 1 on u times du. So we've got ln u technically absolute value of u, but I don't think your lecturer mentions that. 1/3 x cubed plus c. And now, because I know I've finished that, I can put the y back in. So I have ln y squared plus 3 is that. And all I have to do, all in inverted commas, I have to do is figure out what y is. So start as far away from the y as possible, get rid of the ln, and the way to do that is to do e to the power of. So y squared plus 3 is e to the power of all of this. And remember, the plus c is included in that. Now this is where the whole making new constants is extremely useful, because we can rewrite this as e to the 1/3 x cubed times ec, because plus up in the power is times down below. Okay, that's expanding out powers. You know that when you multiply, add the powers. So that e to the c, I'm going to give that a new name, and it will be a constant of its own. Okay? And it's going to be much easier to figure out what a is than it would be to figure out what c is, because I won't have to do ln. So now the next thing to get rid of is the 3. And the next thing to get rid of is the squared. Now technically it's actually plus or minus. I don't know which one it is. It could be either. It can't be both. For those of you in Maths 1A, this is the previous seminar still going, so for a different course. Technically it's plus or minus. I don't know which one it is. I'll have to figure that out in a minute when I put the x in. So let's see. When x, we know that y of 0 is equal to 1. So that means that if I sub in, so x equals 0 means that y is equal to 1, right? So I can sub both of them into this formula and see what I get. In fact, I can sub them both back in here, but I need to know what's going on. So I get 1 equals is that. That's 1/3 times 0 cubed. And we now know it's plus, because that's a positive number there. Okay, so must be the plus. Okay, so we know that 1 is root a, and e to the 0 is 1. So now I can figure out what a is. A is in fact 4. If I had tried to find c, I would now have to do ln, and c would be ln 4, and that's much worse. So now finally, y is equal to plus 4e to the 1/3 x cubed minus 3, and that's the final answer. So they call that a particular solution because there's no constants left behind. Right. Well, you can still come to the Maths Learning Centre, obviously, if you have any more questions. Good luck with your exam. And if I see you in the next couple of days, I will continue to say that good luck, and might see you around. Thank you.